Hello, Ross. For lesson 2.3, there's a couple of applications we don't always get around to in class. If we haven't, if we happen to have the chance to do that, a little bit more review can be useful. I want to take a look at, from the printed lessons online, example 4 and example 5. Example 4 is a question that for right now is probably an extension level question, but we'll have an entire lesson on working with lines tangent to curves. We are equipped to do it right now. It'll just take a bit of thinking on our part. The question can also be worded in a couple of different ways. I'm going to start with a sketch just for organizational purposes. It does not need to be accurate. I mean, I can be pretty accurate with H here. The other thing that I think you'll find the sketch useful to visualize is that often students in this question, the easiest way to get a wrong answer here is to just start to figure out what h prime of 1 is. You'll see on your sketch that you're not interested in what the slope of the tangent to h is when x is equal to 1. A is not on h. Notice that h of 1 is not negative 5. H of 1 is negative 1, I think. A at 1 comma negative 5 is like down here. Okay. So another way that this question could be worded is that tangents are drawn from H and they pass through the point A. At what point do they intersect with H? Or a line is, lines passing through A are tangent to H. Where will they be tangent to H? Lots of different ways of writing it. And this is how I like sort of visualizing this question as well. There are an infinite number of tangent lines to H, right? Here's a couple of them. Like that. There's an infinite number of them. There's also an infinite number of lines passing through A. Here's a couple of them. Like that. Now, to sort of illustrate what we want to happen in this question, let me illustrate a situation that doesn't satisfy the conditions. Notice that right here, this point right here, let this point be on H, and I'm going to move this point P around. Well, right here, if P is placed right there, then the slope from A to P is not equal to the slope of the tangent at that instant. And that's how I know that P isn't going to be one of these points of tangency. I think when we just draw what we want to happen, we sort of lose track of the special condition that we want to occur. So a couple of ways of thinking about this. Turn all of these lines through A until they're no longer secant to H, but until you find it being tangent to H, bing, right there. Or think of it like this. Draw all of your tangents to H, bing, there's one. And then stop when you find one of those tangents that actually goes through A. There it is right there. So these are the 2 points of tangency that I'm looking for. But notice how I'm sort of losing track of the fact that there could be, I could think of there as being 2 families of lines that are coincident at this time. There's every single tangent and every single line through A, and those 2 lines are lining up right there. So I'm going to focus again on that case where it isn't true. And here's what I'm going to do. I'm going to introduce a general point P that's on this curve. I'm going to make sure I know the coordinates of every point on that curve, and I don't want to have too many variables. So I don't think I want to actually have an X and a Y. That's the first thing that I'm going to do, and I'm going to communicate my reasoning. The directions to a question like this will usually say, as always, justify algebraically, because you should always be justifying, but it's a reminder that you're expected to tell your reader what you're doing and announce what you're doing in this case. So I'm going to set P to be a point on H. That means that the coordinates of the point P are going to be A, comma, you could call it P of A. But now, right now, I feel like I have, or even A, comma, B. That'd be too many unknowns. Even P of A is a different unknown than A. Let's try substituting into H. Notice that, or sorry, it'd be H of A. Notice that H of A is going to be 2 less than the square of A. This is really important. Two things are important here. One, I'm not using the variable x, which represents every single point on here, every single value. I'm using a different letter a that represents some unknown value. Okay, x is a variable, a is an unknown. It's different. And the other thing to point out, notice I'm only using one, really I'm using one unknown. So here's p at a comma a squared minus 2. And now focus right here, that at this point, you could call it p sub 2 and at p sub 1, you want the slope from a to p to be the same as the value of the derivative. It'll be equal to h prime of a. So I want you to tell me that you're doing that as well. I want you to set the slope from a to p to be equal to h prime of a. In other words, here, the slope of the line from a to p is not the same as the slope of the tangent, and that's why that's not one of the points that I'm looking for. How am I going to find the points that I'm looking for? It's an argument you should be able to build on your own and not memorize. It's usually very obvious when a student has tried to just memorize how to answer this type of question. It also doesn't go well. Right? Make sure you can explain your way through this. So this is your key strategy. Review it. Don't memorize it. Review this setup. And now I'm ready to go. Let's find an expression for the slope from a to p. I'm going to do y2. Let me get rid of this right here. I'm going to do y2 minus y1 all over x2 minus x1. So that'll give me a squared minus 2 minus negative 5 divided by x2 minus x1 is going to be equal to h prime of a. Well, maybe I should show up here h prime of x would be 2x. And that means that h prime of a is going to be 2 times a. Again, the difference here, h prime of a is just a slope. It is the slope of the curve, the line tangent to the curve h when x is equal to a. H prime of x, this is a function. That's not just one number. This is an infinite number of numbers. 2a turns out to be 2 numbers, which I think I can predict from my sketch. It said find the points, plural. So, okay, so we've got some prerequisite material here. We're solving a rational equation. A decent way of solving rational equations is to sort of deal with your unknowns in the denominator. While solving inequalities, multiplying by an unknown causes problems. When solving equations, multiplying both sides by a minus 1 shouldn't cause any problems. It's going to give me, what, 2a squared minus 2a. And now I'm solving a quadratic equation. I'm going to subtract a from both sides. Sorry, a squared from both sides. Subtract 3a from both sides. Make sure you know how to manipulate linear equations and make sure you know how to solve quadratic equations. You should be solving by factoring first, because it is so much faster than using the quadratic formula. This means that a is either equal to 0 or a is equal to 5. Let's review what it was that we were asked to find in this question. We were asked to find the points of tangency. So these are the x coordinates of the points of tangency. Let's just substitute these into the original function. H of 0 is going to be negative 2. H of 5 is going to be 5 squared minus 2, or 25, 24, 23. Therefore, 0 comma negative 2, and have I done something? 5 comma 23 are the points of tangency. Yeah, there we go. Let's see if I can fix this so I don't need to record a whole other video. Made a big mistake right there. Let's fix that. Okay, how about we just cross all of that out and go subtract a squared from both sides. A squared, keep minus 2a, subtract 3 from both sides. Well, the good news is that it's still factorable. So let's try a minus 3 times a plus 1 is equal to 0. That means that a is either equal to 3 or a is equal to -1. Looking a little better. H of 3 would be 3 squared minus 2, or 9 minus 2, or 7. H of -1 would be 1 minus 2, or -1. So the points of tangency are 3, 7, and -1, -1. Okay, sort of that. I'm glad I caught. There are other ways of doing this question, but usually students don't communicate what they're doing well. What's most likely is that students accidentally stumble upon a way to get the same answers, and then when I ask them, "What is it that you've done in this question?" they can't answer. So make sure you understand what you're doing. Okay, the other sort of prerequisite skill that I want to review is solving systems, which happens in example 5. So it's just an algebraic question. I mean, we could draw sketches here, but I don't think they're going to be helpful. If f of x is ax cubed plus bx squared plus 3x minus 2, and we know that f of 2 is equal to 10, and f prime of -1 is equal to 14, let's find the values of a and b. So sketching should be a skill that you think about using, or a tool that you reach for relatively quickly. But I mean, in this question, we don't know much about f. So I don't know that sketching f is going to be that useful. We should be ready for graphic interpretations of this question. I suppose if I said the function is at a height of 10 when x is 2, and the slope of the line tangent to the curve is 14 when x is equal to -1. We should be able to read it that way. Okay. I'm seeing sort of two clues here in an equation where I have two unknowns. I feel like I kind of need to use those two clues. And graphically described questions, we're going to have to be sort of digging for those clues. But in this question, all we need is an expression for f of x. We got that. An expression for f prime of x. Let's get that. F prime of x would be 3ax squared plus 2bx plus 3. And now I'm going to use statement 1 and statement 2. I'm going to communicate to my reader that statement 1 becomes, you know what, I'm going to put the constant on the right-hand side. That's usually what happens with systems in this course. I'm hesitant to sort of skip this substitution step. I don't need you to show me every single substitution you make in this course. Because I mean, like, it would be nice if we could have sped this up to 2 cubed is 8 times a. Well, that's 8a plus 4b plus 6 minus 2 equals 10. But notice we do have like other collection to do here. Instead of collecting, I think I'm going to divide both sides by 2 first. It's going to make my numbers smaller, and I find smaller numbers are usually a little bit easier to deal with. I wonder if I'm going to have another simplification. I don't think so. It's going to be 4a plus 2b. That's going to be 2. I subtract 2 from both sides, and I get equals 3. Yeah. And I'll call this statement statement 3. Okay, I feel like I've exhausted this clue. I've gotten all the way down to some sort of constant relationship between a and b. I can't solve for a without knowing b, and I can't solve for b without knowing a. I can't solve for a or b without having another statement, another fact that relates a and b. Luckily, statement 2 will give me that. Can I squeeze it in on the side there? Let's find out. Statement 2 tells me that, I'm going to regret this, 3 times a times -1 squared plus 2 times b times -1 plus 3 is going to equal 14. Okay. Let's tidy that up. How about 3a minus 2b equals 11? That wasn't so bad. And now I have two equations on two unknowns. We may be familiar with the methods of substitution and elimination. I really want to stress substitution as being the better option. So when we end up with linear equations of, or sorry, linear systems of three equations on three unknowns in this course, substitution becomes pretty messy. And elimination is sort of the way to go when you're working with matrices as well. So I'm going to announce what I'm doing. This isn't required, but I like doing this, especially later in the course. If, for example, I'm trying to eliminate one variable and another variable happens to be eliminated, I want to keep track of that. So I mention my goal. I'm eliminating B, and then I tell my reader, this is required. Tell your reader how you're doing that. I'm going to do statement 3 plus statement 4. Some students require a bit of review here. If this statement is true and that statement is true, then this plus this will be equal, or sorry, this plus this will also, or sorry, this plus this equaling this plus this will also be true. Okay, just take two statements that are true. This is going to look weird. Let me see if I can come up with a non-silly version of this. 1 plus 3 is equal to 4. That's true. 2 plus 3 is equal to 5. That's true. This means that 1 plus 3 plus 2 plus 3 should equal 4 plus 5. Is that true? 4, 5, 6, 7, 8, 9, and that's 9. Yeah, that's not a proof, but it's a demonstration of the fact that you are allowed to actually add left sides and add right sides and have the statement still be true. Okay, 4a plus 3a is going to be 7a. 2b plus negative 2b eliminates to plus 0b. 3 plus 11 is 14. And you shouldn't feel like you're definitely have done this right just because 14 is divisible by 7. So you're not always going to get integer values, but it happens a lot as well. Now that we have the value of a, let's just communicate that we're going to take that and substitute it into probably one of statement 3 or 4. Easiest way to solve for b, I'm going to put it into statement 3. That means that 4 times 2 plus 2 times b would be equal to 3. That means that 2b, that's 8. 3 minus 8 is negative 5. Oh, here we go. See, don't be too attached to integer values. The fact that you get a rational value, a fractional value, for b doesn't mean that you've done things wrong. And I'm not sure that much of a conclusion is required here. The question didn't ask me to find the function. It just asked me to find the values of a and b. There's a, there's b.